Alright, what's going on, you guys? Another LeetCode video today. This problem is called combination sum. So we're given an array of distinct integers called candidates and then a target integer target, and they want us to return a list of all of the unique combinations of candidates where the chosen numbers sum to target. And then the answer can be in any order. Key part of this problem is that we cannot, or we can choose the same number from candidates an unlimited number of times. So we can use those numbers however many times we want. And then two combinations are unique if the frequency of at least one of the chosen numbers is different. So the order of the numbers in a combination doesn't matter. It's just the actual numbers that you're choosing. So hence combination. Just looking at these examples, we can see that if they give us 2, 3, 6, 7, and then the target 7, there's two ways we can sum up to 7 using those numbers and candidates, right? You can add 2, 2, and 3 together, that's 7. You can also just return 7 by itself, that's also sums up to 7, right? So only two combinations there. You can have examples here. There's another example where this really shows that you can use these numbers an unlimited number of times. I mean, we did repeat a 2 here in this first example, but in this example, if you have a 2 here in candidates and a target of 8, you could literally just sum 2 with itself, over and over again until you get to 8. So that's kind of another key idea to this problem. So we're going to go ahead and solve this with recursion and backtracking. So let's just get into that solution. So if we were given, let's look at that first example. So we have 2, 3, 6, and 7 for our candidates array, and then our target is 7. So basically in our recursion, we're going to have the first call is going to have an empty set, and then it's going to have an empty set at first, and then we're going to have an index that's going to allow us to keep track of where we are in this candidates array. So that'll be 0 at first. So, and then let's label that as I. So this is an index, this 0, this is a set, those brackets. So with our first recursive call, notice how we can choose, remember how we can choose any of these numbers from candidates as many times as we want. So what we're going to do in our recursion is we're not going to increment this index at all in our recursion, and that's going to enable us to be able to basically choose these numbers as many times as we want. So we're gonna, for this first recursive call, we're gonna add a 2 because we're gonna add whatever number from candidates the index corresponds to. So we're adding a 2 here. Okay, and then our index stays the same. Okay, and then we're basically checking, is this the sum of our subset, is that going to be too big or too small or just right? Or, right now it's too small, so we can basically keep doing things with this level of the recursion. But let's backtrack first because this is a backtracking problem. So to backtrack, we'd actually remove this 2 from the set, and then we'd increment the index for the next call. So that would look like this. We'd backtrack by removing that 2. We'd increment the I, so we're adding the next element. So we'd add a 3, and that's just by itself for now, but we do increment the I there. So same thing, we're basically going to have, at this level of recursion, we're going to be trying all the numbers 0 through 0 through index 3, right? So we would backtrack, add the 6, and then that index would be 2. And then finally, for this level of the recursion tree, we'd have a 7 after backtracking, and then the new index there would be 3. So that's pretty much it for that level of recursion. As you can imagine, the height of the tree could be, you could keep going down, adding 2, because that's what's really going to happen here, right? It's like, and let me do this nicely actually. So we'll just see what happens if we went all the way down this way. So, right, we would add a 2 that I does not get incremented, right? So we're basically checking, the sum of these numbers. How do they compare to this 7? So we're not big enough yet. So you could have another call this way where you're not increasing the I at all and just continuing to choose the same element. So we can choose that 2 again. We don't increment I. And we could do this yet again, right? But the way I'm going to implement this is actually, we're going to check if this exceeds the size of target before we call the recursion. So we actually won't get down that far. But we would go this way, right? We would backtrack. We would backtrack the 2. So, but let's start from here. So going this way, or actually, yeah, because this is going to get really, there's a lot of ways you can go here that actually don't end up working. So, but the answer would be in here actually. So while we can't go this way because adding another 2 without incrementing I, leads to a sum here that's too big, we can actually go this way with backtracking, right? So we would backtrack off this 2 and then add a 3, right? Like the next element. And while incrementing that I to 1. And then this would actually be the answer because it's equal to the target. And then this is also our other answer here. Now you could go through and fill in this whole tree. The time complexity for this problem is going to be big O of, it's going to be n, because we can have a branching factor of up to n candidates, right? Candidates, we say this candidates array is size n, so it can have a branching factor of up to n. So big O of n raised to the, it's going to be target divided by the min of the candidates. So this is like, I have to write really small here, but but basically, hopefully you can read that. This is big O of n, where n is the number of candidates, raised to, this is all what it's raised to. It's raised to target. So it's target divided by the minimum of all the candidates, because for the recursive tree structure here, right, for our backtracking, we're gonna have to visit every node here in this tree structure, and that can be, the total number of nodes there can be expressed by this basically this expression, right? Because the height of the tree is going to be target divided by the minimum candidate, right? Because like imagine, so if target is 7 here, we can see that the deepest branch of this tree is going to be 7 basically divided by that smallest candidate, right? Because we have 2 here, 2 here, 2 here, and that can keep going as many times as it takes to sum up to 7, right? So that's the time complexity, and then the space is going to be just that actual greatest depth of the tree, right? Because again, the height of a tree is expressed by log base 2 of the total number of nodes in the tree, and if this is the total number of nodes in the tree, target, and actually it's log base the branching factor of the tree, so this would actually be n, and then that just simplifies to this exponent. So let's just go ahead, I think that's pretty clear. Let's write that. So it's big O of n to the target divided by the minimum of the candidates. So yeah, that's pretty much it for the algorithm. It's for the whiteboarding for the algorithm. So let's go ahead and implement it. So we're gonna need a couple things, right? We're gonna be returning a vector of integers, right? So let's initialize that. We'll just call it result, or res for short. It's gonna have 0 elements in it at first, so that's why I'm passing in 0 there to the constructor. It isn't essential, but I think it's indicative of what we're doing to other programmers by specifying that. So we also want a vector for the current combination we're looking at. So I'll just call that combo. That's just a vector of integers, and it's going to be of size 0 as well. I'm going to do a function overload to implement the recursive function. I'll give it the same name, combination sum. It'll just have different parameters, and then we're just going to return result at the end of that. So let's write the function signature here so we know how to seed that function. So it'll be private. It'll return void. It's also called combination sum. We're going to take a vector of integers for the result. So that's going to be by reference. We also need the current combo, right? So that's going to be a vector of integers, and that'll be by reference. We also need a vector of integers for the candidates. That'll be by reference also. And then we need an integer for that index, so we know where to start in our for loop, and then that should be it. We also need a target, right, to know how we're doing in our current combination compared to the target we're trying to sum to. So that's it for the function signature, so let's go ahead and see that. So we pass in the result first, then the combo, then the candidates, and then the index, which is going to be just 0 at first, and then the target, which we can get from this function's parameters. So that's it for the function signature. So let's implement it. So the first thing we can do is just check, and I'll actually just subtract from target every time we add a number to our current combination. So let's just check if target is equal to 0 to determine if we've have a good combination. So if target is equal to 0, we can just append, or we can push back the current combo to the result array, and then we can just return from this part of the recursion, because we can no longer add elements to our combo, right? It's going to get too big, so we want to return after that. Okay, so then we can just do our for loop, right? So we'll say we'll loop from that index we passed in I to the size of candidates. So we'll say j equals I. Well, j is less than candidates dot size, then j plus plus, and then we're only going to do anything if our candidate, so we'll say if candidates j, we only want to do anything if candidates j plus or candidates j. A better way to do that is actually it's candidates, so target minus candidates j, right? If that is if that ends up being less than 0, then we don't want to do anything, right? So So targets minus candidates j has to be greater than or equal to 0 to continue, right? So that's basically what we're looking for. We basically just want to make sure we're not adding a candidate to our combo that's going to exceed the target we're looking for, because there's no point doing recursion past that point. So, but we do want to do it here when that condition is met. So when that condition is met, we can just go ahead and take our combo vector and then push back the candidate j to that vector. Then after that, we can call our recursion, so combination sum. So we pass in the result, the combo, candidates, and then we want to, we're just passing in j without incrementing, right? Because we can select from those elements unlimited times, right? And then we pass in the, let's see, so it's the index, and then that last value is just the target. But this is going to be target minus candidates j, right? Because we want to keep updating that to see how we're doing. We don't want to have to sum through the combo every time, because obviously that's a linear operation and we don't need to do that. We can just keep track of how we're doing by updating the target. So now for the backtracking, we'll just combo.pop back, and that handles the backtracking step. So that's pretty much it for the code. Let's go ahead and run this. So hopefully this video was helpful to you. If it was, leave a like and subscribe, and I'll see you guys in the next piece.